Okay, in this video we're going to do number 6 from the 2019 Calc BC exam, and it's the series question like it pretty much always is. And so we are told that a function f has derivatives of all orders for all real numbers. We're given a portion of the graph of f, so that graph over there is the graph of f. And we're also given a table of some values, and for the first part we need to write the third degree Taylor polynomial for f about x equals 0. So to do that, we're going to need to know f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. So double and triple prime are in the table, and I need to use the graph to find f of 0 and f prime of 0. So if you look at that point, you can see that f of 0 is definitely 3. And then using the tangent line here, you can see the slope of that line is down 2 over 1. So f prime of 0 is negative 2. And so we're going to use the formula. So I'm going to write it all out. So f of x is approximately equal to, because we're only using the third degree, we're not going to infinity. So it's the value at 0 plus the derivative, and then x minus 0 to the first, plus the second derivative over 2 factorial, x minus 0 to the second, plus the third derivative over 3 factorial, x minus 0 to the third. I'm really just writing that out for the purpose of the video. You don't have to write that out when you write your solution. And now it's just substitution. So we know all of the values. So f of 0 we found to be 3 up there, plus f prime of 0 we found to be negative 2. And then I'm going to simplify the x minus 0s to just x. So that's x to the first. F double prime we get from the table. So f double prime is 3, so plus 3 over 2 factorial, x squared. And then f triple prime is negative 23 halves, which is kind of weird. So I'm actually just going to write that there. We're going to have a complex fraction. And then the x cubed. Okay, so that's actually part A. We don't have to simplify this at all. So let's move on to part B. So we actually need our solution from A in part B. So I copied it over. We want to write the first 3 non-zero terms of the Maclaurin series for e to the x. Okay, so that's just from memory. So e to the x is approximately 1 plus x squared over 2 factorial. You can keep going forever with that pattern, but we only need the second degree. Well, we need the first 3 non-zero terms, I should say. And the next thing is we want to write the second degree Taylor polynomial for e to the x times f of x. So we're going to have to multiply some polynomials, basically. So e to the x times f of x is approximately, so we're only going to the second degree. So at most I need the second degree polynomial for f and for e. So e we just wrote. And f we need at most the second degree. So I'm going to just leave off that cubic term, like that. And now I'm not really sure. I think you probably have to expand this. I'm going to expand it for sure because I'm not positive. So we get e to the x, f of x is approximately. So to multiply these, it's just like an algebra 2 or algebra 1 problem. I'm going to multiply everything in that second parentheses by 1 to get this. And now it gets a little trickier because we only want the second degree polynomial. So I'm going to take x and multiply it through, but then x times the x squared term I'm just going to leave off because that would be too high a degree. So I get 3x minus 2x squared, and then I'm skipping that last one because that would be cubic. And then for the next part, I actually only need to multiply this by 3 because anything other than 3 will just be too high a degree. So we multiply there. This I think you could leave, but I'm going to simplify it. I kind of just like simplifying these things. So I get 3, and then just plus an x, and then this I'm just going to write like this. And we could be done there, but why not? So if we simplify this, we get 3 plus x, and then plus x squared. So that's a second degree, second degree polynomial, Taylor polynomial for e to the x times f of x. All right, let's do part C. So again, we need this, and also I'm going to actually end up simplifying it here. So let h be the function defined by h of x is the integral from 0 to x of f of t dt. So we have this, and we want to use the Taylor polynomial from part A to find an approximation for h of 1. Okay, so h of 1 is going to be the integral from 0 to 1 of f of t dt. And so at this point, I simplified f of t a little bit because I need to reverse the power rule and it's just simpler. So that negative 23 over 2 over 3 factorial, I rewrote as negative 23 over 12. And now it's just a fundamental theorem. So h1 is approximately, so 3t minus t squared plus 1/2 t cubed, because the 3 and the 1/3 cancel. And then minus 23 over 48, because 12 times 4 is 48, t to the 4th. And then we're going from 0 to 1. So now when you plug in 1, all the t's just kind of, go away. When you plug in 0, it zeroes everything out. So that's going to be my approximation for h of 1. I'm actually not going to simplify that one because that seems like it'd be annoying and we don't have to. So I am going to move on to part D. All right, so part D, I'm bringing the table back because it's a long one. Let me read it. So it's known that the Maclaurin series for h converges to h of x for all real numbers x. Okay, so it's just known. It's also known that the individual terms of the series for h of 1 alternate in sign and decrease in absolute value to 0. So that means it's a convergent alternating series by the alternating series test. Use the alternating series error bound to show the approximation found in part C differs from h of 1 by at most 0.45. So this is just alternating series error, but it's like super wordy. All right, so the first thing I know is that the alternating series error is less than or equal to the absolute value of the first term that is left off. In this case, the first term left off is going to be a little bit of work to find. So this was the f of x that we used in the previous part. So I used the entirety of that polynomial. So the first term left off, I actually need to figure out. So I'm going to need the next term in this polynomial, which should be the fourth derivative over 4 factorial x to the 4th. Okay, so that's my first term of the polynomial that I left off. So I'm now going to kind of do the problem, I guess. So h of 1 definitely converges by the alternating series test. They gave us all of the conditions that we need. Therefore, the error is less than or equal to the absolute value of the first term that we left off. So we used everything and we integrated from 0 to 1. So the first term that we left off would be the integral from 0 to 1 of that first term that we left off. So we get this. And now it's kind of, so that's definitely positive, so I can drop the absolute values. I'm just integrating, so plus 1 times the reciprocal gives me 4 factorial times 5, which I'm writing as 5 factorial, which I don't know if I'm going to regret that. So then the error is less than or equal to 54 over 5 factorial, because when you plug in 1, you get 1. When you plug in 0, you get 0. We need to show that this is less than or equal to 0.45, which I'm guessing that it just is. So 54, I'm going to make 6 times 9. And then 5 factorial, I'm going to write as 5 times 24. And the 6 and the 24 cancel, so we get 9 over 20. And 9 over 20 is 0.45. So we showed that the error is less than or equal to 0.45. All right, so that's the end of the problem. I hope you found this helpful, and good luck.